Okay, so this is a lecture on related rates. It's an application of implicit differentiation, which we learned, just had a quiz on that last week. And what we're going to do is we're going to relate the rate of change of two related quantities, like the area of a circle and the radius of the circle. So if we know so if we're told that the radius of a circle is increasing or decreasing at a given rate, what is the area of the circle decreasing or increasing? Okay, so let's just quickly review implicit differentiation. Let's just look at B here. So let's say you have that expression 5x cubed, and you take the derivative with respect to time. And so we take the derivative. We know the derivative of 15x squared, 15x cubed is 15x squared, but x is a function of t. So then we apply the chain rule. We multiply it by dx dt. That's what we have right there in part B. And you can see something a little more complicated, C. Take the derivative with respect to time, and you get 15x squared dx dt times 2y dy dt. And so let's look at our first related rate problem right here. And so to some degree, we're actually not learning anything new because it's just an application of the chain rule. But let's say we have this expression, we have that formula, xy is 4, so y is 4 over x. If you graph that, you get a hyperbola. Yeah, so as that y decreases, x increases, for x and y are positive. Okay, so it says find the rate of change of x when x is 8, and the rate of change of y is -2. We're actually not giving units there. Okay, so when x is 8, you just use the function formula, or that hyperbola, xy is 4. If x is 8, y has to be 1/2. And now let's take the derivative of xy with respect to t, and we're going to use the product rule. So it's x dy dt plus y dx dt. And so what are we trying to find? Okay, so we're trying to find dx dt, and we're given dy dt. And we also are given this, relationship. You have to have some relationship between x and y, or else, there's no problem to solve. Okay, so we use the chain rule, and we know that x is 8. When x is 8, we know y is 1/2. And we're given that dy dt is -2. Now solve for dx. And you solve for, now it's just, you have these 4 variables here, like x, dy dt, y, dx dt. The only one that's unknown is dx dt at this point. Okay, so when x is 8 and dy dt is -2, when x is 8, y is -1/2. So now just like solve an equation, and we get dx dt is 32, which kind of makes sense, physically it makes sense. When y is decreasing, for positive x, when y is decreasing, x has to be increasing, right? Just look at the graph. As the second coordinate goes down, the first coordinate, is just going way out there to infinity. Okay, so I actually did, so there's actually many more problems in here. I did a few from the homework, so I'll talk about those. Just some things just to remember, things that are just in general useful for word problems. Okay, so I think this part C here is really important. So you might even just want to write that down. What are you trying to find when you have a word? Because we're going to have more word problems after the break, after exam 2. I think it's a chapter 4. So there's going to be problems in optimization, where you're going to have, you have to write formulas, and which of those, what variables are you, trying to solve for. And so we have to know, what are we given, what formulas do we know, and then just find out what we have to find. So I think especially this part C is especially important. What is it we're trying to find? Because some of these word problems, they're very similar, and sometimes they sound alike, but we're trying to find different things. Well, I guess we'll see that more as we go on. Okay, so let's look at this problem 3 from the homework, and the numbers might be different. Okay, so we're talking about an isosceles triangle. So an isosceles triangle is a triangle where the legs are the same, are identical, and so it's a right triangle. Okay, so let's look at this first part. And what are we given? We're given that the legs are increasing at 4 meters per second squared. So it's positive 4 meters per second squared. Okay, so what rate is the area of the triangle changing when the legs are 1 meter long? So we know that, the leg is changing. The leg of a triangle is changing at 4 meters per second. And so when the legs are there, when the legs are 1 meter long, what is the rate of change of the area? Okay, so well, we need to somehow relate area and the side of the triangle. Okay, so right, so we're just using that right triangle formula. You know, x each side. Whoops, it doesn't look like an x to me. I'll try to draw. Okay, so each side is x. Okay, so the area is 1/2 x squared. So here's your formula: 1/2 x squared. Now, and we know that we know x and we know dx dt. So let's just find dA dt and plug in these values. So dA dt, I take the derivative, drop down the 2, multiply it by 1/2, and then apply the chain rule. So you know that dA dt is x, the length of one of the side, the length of one of the legs times dx dt. Okay, so now when the leg is 1 meter long and dx dt is 4 meters per second, what is dA dt? What is the rate of change in the area? This one's pretty straightforward. You can just plug it in. Substitute 1 for x, and for dx dt, substitute 4 meters per second. So dA dt is 4 meters per second squared. So let's just be careful about the units. Okay, so the rate of change in an area, well, area is two-dimensional, and time is going to be, it has to be like an hour or second or something like that. But yeah, in this case, we know that the at least the numerator, that meters squared, that's two-dimensional because area is two-dimensional. Okay, so just make sure we use. So if we want meters per second, that wouldn't make any sense. Okay. Okay, so let's look at this second part here. When the hypotenuse is 6 meters long, we want to know what the rate of the change of the area is. So I think I did this down here, and now I just used I use this. I guess they asked for this in part C, but we use it right here too. So this is just the Pythagorean theorem here. So we get okay. So when the hypotenuse is 6 meters long, the area of the triangle is changing at the rate of. So and this is what we have to find. We have to know when h is 6, what is dA dt? Okay, so let's just find a relationship between dA dt and h, and it turns out so we using the Pythagorean theorem, we get 2x squared is h squared. Okay, so and so when the hypotenuse is 6, what do we get for, we get x is 6, we have to solve for x, right? Okay, so when the hypotenuse is 6, we get this relationship between x and h. Okay, so when h is 6, x is square root of, we just solve for x. X is equal to h over the square root of 2, or x is equal to 6 square root of 2 over 2. Okay, so so again, we're trying to solve when the hypotenuse is 6. What is dA dt? Okay, so let's find out what the length of one of the sides is when when the hypotenuse is 6. We get x is 6 square root of 2 over 2. And again, we're going to have to use that formula from part A. dA dt is x dx dt. In this case, when the hypotenuse is 6, we know that the legs are 6 square root of 2 over 2. And the rate of change of x is still 4 meters per second. So the leg is 6 square root of 2 over 2. The rate of change of one of the legs is 4 meters per second. And you plug that in and you get 12 square root of 2 meters per second squared. Okay, then for part C, we already kind of did it. Write an equation relating the length of the legs of an isosceles triangle X to the length of the hypotenuse of the triangle H. Again, you just use the Pythagorean theorem, because the sides are have equal length. The legs have equal length, so you get 2x squared is equal to h squared, and you solve for h, and you get h is equal to x times square root of 2 over 2. And so you want to know, so what is the rate of change? The problem is, what is the rate of change? The length of the hypotenuse is changing at the rate of. So what is the legs are changing at the rate of 4 meters per second. How is the hypotenuse changing? Well, we have this formula between h and x. First, from the Pythagorean theorem, we get h is equal to x squared times square root of 2. Use just take the derivative of both sides with respect to h, respect to t. So you know that that the rate of change of h is dH dt is dx dt times the square root of 2, And when dx dt is 4, the rate of, so when the legs are changing at the rate of 4 meters per second, the hypotenuse is changing at 4 times square root of 2 meters per second. Okay, so let's just look at another problem here. So let's look at number 7. This is the one with someone going fishing. And so this sometimes this looks maybe look more complicated. You have this picture here, but it's really all it is. It's a right triangle problem. Okay, so so we want to know, okay, so someone's going fishing and they're pulling this fish in, and so what is the rate of, what is the speed of the fish? When the fish is 16 feet from the I guess the angler. I don't really know a lot about fishing. Okay, so so I assume the angler is the person fishing. Okay, so this is x is the distance here. So we're told that they tell us what variables to use. So x is the distance, the horizontal distance of the fish from the fisher person, and z is the length of this line here. And so you can see how there's this pole, the fishing pole is straight up, and then then the line, the line from the pole to the fish is called z, and that's the hypotenuse of the so z is the hypotenuse. The length of the line is the hypotenuse of this right triangle, and we're told the pole is exactly 11 feet. Okay, so be careful here, and I think I even kind of messed this up when I first did this problem. It says find the horizontal speed. Remember, speed is the absolute value of the velocity, right? So I think I initially entered a negative value because I wasn't paying attention. I was trying to find a rate, but remember, speed is has nothing to do with direction. Okay, so x is the horizontal distance, and the height of the pole is 11, and z is the length of the line. And so so I actually did a lot of the problem down here. Okay, so again, it's just a right triangle, and and also what makes it this also a little bit tricky is the rate is given in terms of inches per second, but some of the measurements are given in feet. So let's convert 11 feet into inches. So 11 feet multiplied by 12, you get 132. Okay, so the right triangle formula tells us that we get this relationship between the distance of the fish from the fisher person and or the angler, I guess, and the length of the line is 132 squared plus x squared is equal to z squared. Okay, and so so that's the relationship between x. So we're looking for the absolute value of dx dt. And we're told that dz dt, we know that dz dt is, I can't say that, dz dt is 5 inches per second. It's hard to say. Okay, so let's just take the derivative of both sides here. So we have this relationship between x and z, and now we're going to use implicit differentiation, take the derivative of each side with respect to time, and we get 2x dx dt is equal to 2z dz dt. And they actually kind of step us through the problem, and we're actually told, we have to do that right here. Okay, so then when the fish is 16 feet from the angler, remember that's 192 inches, we have to find the horizontal speed, or the absolute value of dx dt. Okay, so so dx dt, so we just solve right here. So using it, so we have the relation between x and z is that right triangle formula. Take the derivative of both sides, you get 2x dx dt is equal to 2z dz dt, and you solve for x, or I'm sorry, we want to find the absolute value of dx dt. So dx dt is z over x times the rate of change of the line. Okay, so when x is 16 feet or 192 inches, okay, so then, so also we have to know what z is, right? Okay, so you can plug, okay, what's the z? Well, remember, you have this right triangle formula here, right? So I'll just do this in terms of, well, no, we'll just do this in terms of, so remember, this is 132 inches, and this is 192 inches, right? So what is z? So, and I'm sorry, the height is actually 121 inches. 11 feet, 121 inches. X, the distance of the angler from the fish is 16 feet or 192 inches. Okay, so again, we're just going to use the right triangle formula. And we're going to get that so when the fish is about 16 feet from the angler, we get the length of the line is the square root of 121 plus 192. And so we're going to approximate to 2 decimal places. So we get about 233.04 inches. And now we can find the rate of change, how the distance is, so the distance is changing at when x is 16 feet and dz dt is dz dt, let me just remember, is 5 inches per second. Okay, so you just plug in this formula. Remember, we found this formula here. Remember, x squared plus y squared. I'm sorry. Remember, we had this formula: 132 squared plus x squared is z squared. Took the derivative of both sides. Solve for dx dt. We got dx dt is z over x dz dt. Okay, we found that when x is 16, 192 inches, we get that z is about 233.04 inches. And you just plug this in, and you get the rate of change of x is 233.04 divided by, this is all in inches, divided by 192. And the rate of change of the line is 5 inches per second. So the rate of change of x, okay, so when the line is decreasing at 5 inches per second, the fish is 16 feet from the angler, and the pole is 11 feet high. You get that the rate of change of the distance of the fish from the angler is negative 6.07 inches per second. But remember, we want the speed. So, so the answer is, you take the absolute value. The speed is 6.07 inches per second. And that's approximation, but I think it's a pretty good approximation. Okay, so then the last one, is this one of our favorites here? Okay, so the last one. Okay, so a woman walks towards a streetlight at 4 feet per second. And for a streetlight that is 15 feet above the ground, okay, what is the rate of change of the length of her shadow when she is 16 feet from the streetlight? Okay, and what rate is the tip of her shadow changing? Okay, so I did all of this kind of below the problem. Okay, so let L be the length of the woman's shadow and X be the woman's distance from the streetlight. Write an equation that relates L and X. Okay, so now we're going to use what we learned maybe from our trigonometry class a long time ago. And so we just use the this ratio here, that 15 is to, so you have these two triangles, these two similar triangles, right? You have one that's, so we're trying to find a relationship between the distance of the woman from the light and the length of her shadow. When the height of the street, when she, the woman is 5 feet tall, is that right? The woman is the woman is 5 feet tall, and the height of the light is 15 feet. Okay, so so you have these two similar triangles. So you have this 5 and L here, and then you have the other one that's 15, and the length of and this is L plus X. I'm trying to write on the screen. It's a little bit hard. Okay, there's similar triangles. So we have 15 is to L plus X. 15 divided by L plus X is equal to 5 over L. And so now you just solve for L. 15L is equal to 5 times the expression, a quantity L plus X. To solve for L, you get 10L is equal to 5X, or X is equal to twice L. The distance of the woman from the light is equal to twice the length of her shadow. So now we have a relationship, right? So we need some relationship between the distance of the woman and the length of her from the light and the length of her shadow. Otherwise, we really can't, because what we're trying to do is trying to find, find a relationship between how fast the shadow is changing, the length of how fast the length of the shadow is changing, and the distance of the woman from the light. So now we have this relationship between the distance of the woman from the light and the length of her shadow. And now part 2 says, well, let's just differentiate both sides. So, okay, so we know that that's a pretty easy derivative to take. Dx, so the rate of change of the distance of the woman from the light is equal to twice the rate of change of the length of the rate of how the shadow is changing. Okay, part 3, or we can solve for dLTT. The rate of change of the shadow, the length of the shadow is 1/2 the rate of change of how far the woman is from the light. Okay, so now let's see here. Okay, so again, so what we're trying to find is, again, what is the rate of change of the length of her shadow when she is 16 feet from the streetlight, given that she's walking at 4 feet per second? So we're trying to find, again, this is one of the important, we have to make sure, these problems in the homework kind of step you through this, so we make it a little bit easier. Normally on a, you don't necessarily have all these steps, like if you were actually taking a test in class or something, but what is the rate of change of the length of her shadow when she is 16 feet from the street? And of course, it's really important that we draw that kind of, that picture right there. So we're trying to find we're trying to find dLdt, given that x is 6 and dx dt is 4. Okay. So the last part here, okay, so so we want to find dLdt. Okay, so we found that, so we found that relationship between with the similar triangles. We found that the distance of the woman from the light is twice the length of her shadow. So the rate of change of the distance from the light is twice the rate of change of the length of the shadow, or just solve for dLdt. The rate of change of the length of the shadow is 1/2 times the rate of change of the woman from the light. Okay, so the woman is walking towards the light, so the distance from the light is decreasing. Okay, so that means that dx dt is negative, right? Dx dt, so the rate of change, so the distance is changing at a rate of minus 4 feet per second. So we just plug this now, okay, so dx dt is minus 4 feet per second. Just plug that into this formula. So that means that the rate of change of the shadow is changing at the rate of minus 2 feet per second, given that, when she's 16 feet away, and the rate of change of the distance from the light is minus 4 feet per second. Okay, so now the second part is the tip of the shadow. Okay, so it says how fast is the tip of let's see right here, this last part right here. So now we want to find the tip of her shadow. What is the rate of change of the tip of her shadow? Now the tip of her shadow is, how far is that? That's L plus X. That's the distance of the woman from the light and plus the length of her shadow. Okay. And so we want to know dL dt plus dx dt. Once again, it's when we assume it's when she's 16 feet from the street light. Well, we already found when she's 16 feet from the street light, well, we're told dx dt is minus 4. And we found that dL dt is minus 2. So you just add them together. And so, yeah, so the tip of the shadow is x plus L feet from the light, the length of her shadow plus her distance from the light. And the rate of change of the tip of the shadow is dx dt plus dL dt. You add them together and you get minus 6 feet per second.